Hey everybody. I wanted to give some solutions to the last quiz because there were some really fundamental skills, particularly on the first problem, that I want to make sure that everyone's on the same page on. So let me go ahead and share screen here. And let's look at that quiz. Quiz number 4. The first question said, let A be a fixed number in R once and for all, and let W be this particular set. We may assume that W is a subspace of P sub n of R. So remember that P sub n of R, this thing here, that's the set of all polynomials with real coefficients of degree at most n. So 1, x plus 1, x squared minus pi, x cubed plus x squared minus 3. These are all polynomials with degree at most 3 that I've mentioned. So for whatever that n is, that's the highest degree polynomial you will see. And then this set W is the really important thing we're going to focus on here. So we said that we can assume that it's a subspace of this vector space P sub n of R, but W is a set of all polynomials in that set satisfying an additional condition, namely that if you plug A into that polynomial, you get 0. So the first question, the first part, asks us to simply observe that this set S equals a set of polynomials, x minus a, x squared minus a squared, and so forth, is a subset of W. So what does that mean? That means that if we look at each of the items in S1, I'm going to call the first one, for instance, F1. F1 of x is x minus a, and I'll call F2 of x. The second thing from S, x squared minus a squared, and so on. Well, these are the things in S, and to be a subset of W means that the things in S are also in W. Everything in S is also in W. All right, so here's a thing in S, F1 of x, namely this polynomial, x minus a. That's an element in S, and we want to show that it's in W. Well, to be in W means that you have to satisfy this condition. So let's see if this polynomial, F1 of x, actually satisfies that condition. What is F1 of A? Well, we plug in A for x, and lo, we get 0. So yes, the condition is satisfied, and that tells us that F1 is in the set W. Similarly, if we look at the second polynomial, F2 of x, we want to check whether it satisfies the condition necessary to be in W. Well, when we plug in A, we get a squared minus a squared, which again is 0, and that's what it means for this polynomial to be in W, that when you evaluate it for x equals a, you get 0. And this is then clearly true for all of the polynomials in this set S, because they're set up precisely so that when you plug in A, you get a power of A minus that same power of A, which is then 0. And now that's what it means to be a subset of W, that everything in S is also in W. So hopefully that clears up some confusion. The second part asks us to show that this set is linearly independent. So let's appeal directly to the definition of linear independence. Suppose we can write the 0 vector, in this case the 0 polynomial, as a linear combination of these objects, these vectors. In this case, the vectors are polynomials. So each polynomial is one of my vectors, and I want it to equal the 0 polynomial, which we usually just write as 0 without even a bar over it or anything. This is the 0 polynomial. You could think of it as the function that is 0 for all x. Well, we would like to then show, if we want to show that the set S is linearly independent, that all of these coefficients must be 0. Well, we can rearrange what we've got, and let's write it in, say, descending powers of x. So x to the n, x to the n is the highest power we've got, and it should only have one coefficient, c sub n. And then what's the next highest power of x? That would be x to the n minus 1, somewhere in there, I suppose. And it would only have one coefficient, namely cn minus 1, x to the n minus 1. This pattern would continue all the way down. Let's see, what is the highest power on x? Well, that's just c1 times x. And then we'd have a constant term. And let's note that there's going to be a lot of constant terms, because cn times negative a to the n, well, that's a constant. And cn minus 1 times negative a to the n minus 1, that's a constant, all the way down to c1 times negative a, that's a constant. So the constant term here is going to be something like minus c1a minus c2a squared dot 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 minus cn a to the n. But no matter, how can this polynomial here on the left be equal to that polynomial over there on the right? Well, the 0 doesn't have any powers of x, so the only way for a polynomial with an nth power of x to be equal to the 0 polynomial is if the coefficient on the nth term is equal to 0. And the only way for a polynomial with a coefficient on the x to the n minus first power to be equal to the 0 polynomial is if its coefficient, cn minus 1, is also 0, and so forth down to the power of x. C1 times x is supposed to equal 0 x's, so that means that c1 is equal to 0. And, well, there's also now this condition that this big fat thing here, c1 a minus c2 a squared, and so on, is equal to 0. But if we know that cn is equal to 0 and cn minus 1 is equal to 0 and c1 is equal to 0, then this whole thing will, yeah, sure, be 0. That's fine. The point is that now we know that each of the coefficients that we started with in our linear combination must all be 0. So this, in fact, implies that S is linearly independent. So for much the same reason that the standard basis for the vector space of polynomials is linearly independent, this set S is linearly independent. Each of the polynomials in the set has a different power of x involved. All right, so finally, the thrust of this problem, the part that actually requires some additional insight, some new information, like the extend to a basis theorem, determine the dimension of W. So let's observe that we have a linearly independent set. S is a linearly independent set in W because we directly observed in part A that S is a subset of W. So this is a set of vectors in W, but it's linearly independent. So this tells us that the dimension of W is going to have to be greater than or equal to the number of vectors in S, which is, well, let's look at S again, x to the first power, x to the second power, x to the third power, up to x to the n power, I guess n of them. There are exactly n vectors in there. Yes? So the hint says we can use the extend to a basis theorem. Let's recall the extend to a basis theorem says that any linearly independent subset of a finite dimensional vector space can be extended to a basis for the whole vector space. So in this case, we have S, a linearly independent set in W, and W is itself a vector space. So I guess we can extend S to a basis for W. So this implies that S can be extended to a basis for W. Let's call it S hat. Well, S already had n vectors, so either S is already a basis for W or it's not, in which case S hat has some additional things in it, we add some vectors. But remember, W is a subspace of this vector space P sub n of R. And the dimension of that we know also, because we know a standard basis for that vector space. The dimension of Pn of R is equal to n plus 1. So if we already have n vectors in S, the most vectors that could be in S hat would be n plus 1. But I guess there can't be n plus 1 vectors there, or else we'd have a basis for this entire vector space. So since W is not the same as this entire vector space, let's think about that for a moment. W is a set of polynomials satisfying this additional condition that if you plug in A, you get 0. But of course, there are polynomials that don't have that property. For instance, x minus 1 if A is not 1. Or x minus 2a, whatever a is, that'll be a polynomial that's not in W. So it's definitely the case that W is not the whole ambient vector space. So S hat must not have n plus 1 vectors. It must have n vectors. Namely, S hat is equal to S, and the dimension of W is equal to n, because S forms a basis for W. There can't be any more vectors in a basis for W, or else you'd have a basis for the entire vector space Pn of R. So the set S must actually be a basis for W. So this is kind of a cool argument. This is a slick point, but it's a nice use of the extend to a basis theorem. And I think it's really especially important that you guys understand how to do part A and part B. So please feel free to follow up if there are any questions. I want to make sure those are very solid as we move on. All right, number 2 asks us to look at the linear transfer, or the function from complex numbers to complex numbers, defined by taking the conjugate of the complex number. And we're told that T satisfies one of the two conditions of a linear transformation, but not the other. And we want to figure out which is which, and prove the one holds that does, and show why the other one does not hold. So the two properties, of course, are that T respects addition, and that T respects scalar multiplication. All right, so what does it mean to say that T respects addition? Well, suppose we have two complex numbers in C. Well, complex number, of course, has the form a plus ib, and maybe c plus id, where a and b are real numbers, and where c and d are real numbers. So then let's ask, on the one hand, what happens to t of z plus w, and on the other hand, we'll ask what happens to t of z plus t of w. Okay, well, as things stand, in order to write down what t does, we need to do something with z plus w. Z and z plus w is not written in this form, a plus ib, so it's not entirely clear maybe how to write down that conjugate. So what we should do is use what we know about these complex numbers, namely the z is equal to a plus ib, and the w is equal to c plus id. And then we can rearrange this complex number into one real part, a plus c, and one imaginary part, b plus d. And now we can see exactly what t does. It switches the sign between the real and the imaginary part. All right, on the other hand, if we look at t of z plus t of w, well, z is equal to this complex number a plus ib by itself. W is equal to this complex number c plus id by itself. And t will just then switch each of those signs individually to a minus ib, and then c minus id. And with just a tiny bit of algebraic rearrangement, we can see that this is the same as a plus c minus I times b plus d, factoring out a negative sign. And so yes, in fact, these are the same. T does preserve or respect addition. So I guess by process of elimination now, we should expect that t does not respect scalar multiplication. But let's see it out. So suppose z is equal to a plus ib, some arbitrary complex number, and I'll call it k is some scalar. Well, the first thing to note is that based on the way the function is defined from complex numbers to complex numbers, we should be able to assume that these scalars are in fact complex numbers. So k is also some complex number. So what we might try to do is look at t of k times z, and on the other hand, look at k times t z. Let's start with this one. K times t of a plus ib. Well, that's just k times the result of applying t, that's a minus ib. And there we are, k times a minus ib. On the other hand, let's look at t of kz. It's very tempting to say that z is just a plus ib, and then try to flip the sign right there alone, except that k is also a complex number. So the real part of k times a plus ib may not just be ka, and the imaginary part of k times a plus ib may not just be k times b, because k itself might have some imaginary parts. So let's be more explicit about that. Rather than just saying some complex scalar, let's say that k is equal to I, a particular scalar. Then what would happen? You can do this with any complex number with an actual complex part. but I think it'll be clearer if we just look at I itself, which clearly has an imaginary part. Then in order to work out what t does, we should rewrite this in the form real number plus I times a real number. Well, a times I is going to be an imaginary part, and I times IB, well, that's going to give us a real part. That's going to be minus B plus I times A. And now when we apply t, it flips this sign between the real and the imaginary parts, giving us minus B minus IA. All right, well, maybe that gives us the same thing down here. Let's see what happens if we took K to be just the number I. K is just the number I. K is just the number I. Well, this is going to give us, ooh, I times minus IB is going to be a positive B. And then we're going to get a positive AI, and these are not the same. So we conclude that T does not preserve or respect scalar multiplication. Finally, there's this bonus question. Prove that if a function f from a to b has an inverse, then f is 1-to-1 or injective, and f is onto or surjective. So let's prove each of these. F is injective. 1-to-1. And we'll also prove that f is surjective or onto. All right, so what does it mean to show that f is injective? We'll say that if we were to suppose that f of a1 were equal to f of a2 for some a1 and a2 in the domain of f, namely a, what we want to do is prove that a1 must equal a2. But because we know that f has an inverse, we can apply the inverse to each side of this equation. And by the definition of an inverse, then, f inverse of f of a1 will just be a1. F inverse of f of a2 will just be a2. And so this implies that a1 must equal a2. So yes, f is injective. Finally, to show that f is surjective, we will start with anything from the codomain B and find an element in A, which gets sent to it by f. So suppose B is any arbitrary element from B. Well, again, since we know f has an inverse, the inverse goes from capital B to capital A. So we can conclude that f inverse of B is a thing, and in particular, it's an element in A. And so we've found the thing in A that gets sent to B, namely f of that thing, f inverse of B. Well, again, by the properties of an inverse, f of f inverse is just the thing in there, that argument in there, so that's B. So now we've found a thing in A that gets sent to B, and so f is surjective. All right, hopefully that was helpful, and I will continue to do these videos if you guys find them helpful.